Chapter 1 was an introduction and some reminders about linear algebra. Chapter 2 is now going to talk about kinematics, which is the description of motion, irrespective of motion and deformation in the case of solid. Without reference to what produced the motion or produced the deformation. There's a lot of vocab and concepts that I have to introduce before we can move on to forces and stresses that create those deformations, right? So that's why it's called kinematics. Okay, so you will see in the lecture note there's a whole page of descriptions about how we're going to describe a body, a solid body, or the body of a solid, if you want, and its deformation from what's called a configuration to another configuration. And instead of going through all those words, I'm just going to draw a diagram to introduce those concepts. So in continuum mechanics, there's often those potatoes. Yeah, just think of a blob, of a solid that's deformable, right? A piece of rubber, a sample of jelly, something like that. And in this course, we consider that a solid is a collection of points, of material points inside the solid, and a continuous distribution of points. And we denote the, let's say, a representative point, the point B inside the solid. We denote the coordinates with respect to an origin, O, and then there's 3 unit vectors. Remember, I introduced them earlier, I believe. Three orthogonal unit vectors, so that I can write the position of the point as capital X is x1, x2, and x3 along each of those vectors. All right, so that's my body. You should think of it as, you know, a free body, free of anything, any load, it's just there. It's my starting point. And then I deform it. I apply forces, I move it around, and it changes shape, and the points are moving away one from another or closer one to another. So that point P is going to move to this location here. And now I'm going to have to introduce another coordinate system because I'm in a different state now with another position vector. I'm going to call it little x, and it is a vector with origin little o, and I'm going to associate 3 unit vectors, little e1, little e2, little e3 in that coordinate system, and write that little x is x1, e1, plus x3, e3. All right, so it's the same body, but it has moved and deformed. And so I'm going to have to distinguish those two states. They are called configurations, right? The one on the left, that's called the reference configuration. I want to call it PR. That's where the body was before I deformed it. And now it's moved and it's been deformed into a new state, which I'm going to call the current configuration. PC. So reference current, that makes sense intuitively. Configuration as well, I think that's okay. And then what you're going to introduce is a mapping of one state to another. I'm going to say that this point here, P, which was at capital X in the reference configuration, has moved to little x in the current configuration through a mapping, an injective function. I'm going to call it chi, and depends on capital X and on time t. A one-to-one mapping. One-to-one mapping. And that's called the deformation. If I specify chi, I'm going to specify a deformation. I could say, I don't know, I could do, for instance, a translation or rotation. I could do a stretch. I could impose it mathematically, or I could impose forces and see what deformation results from that, so on and so forth. In the end, I have this function chi of capital, I call it. It's what links capital X to little x and vice versa, right? There's no creation of points or no annihilation of points. That's why I say one-to-one. There's just as many points in the reference as in the current configuration. And so there's a lot of vocabulary associated with those notions, those concepts, right? And usually here, so that's the usual convention, to use capitals for what happens in the reference configuration and to use lowercase letters for what happens in the, or to describe what happens in the current configuration. And those coordinates, capital X, they are called the material or the reference configurations, or the Lagrangian coordinates. And the little x's, they're called the spatial or Eulerian coordinates. And in this chapter, we're going to see how to go from one to another and how to describe that deformation. So there's a lot of vocab: material, reference, Lagrangian, current, spatial, Eulerian. You will see that in this course, there's a huge amount of vocabulary. And there's no agreed convention, because all of those things are equivalent. Some people prefer that word, other people prefer the other word. And all of those concepts are also equivalent, and there's one-to-one correspondence between each of them. Maybe for some problem, it's handier to use this formulation. For another problem, it's handier to use the other. So we need to know all of those notions. Okay. The deformation. And if it depends on t, it's called the motion or moving deformation. Okay, I'll just give you a very simple example of a deformation, a rigid motion. When the distance between any 2 points remains unchanged. All right, 2 points in the body, they are at a certain distance one to another, that are moving, maybe they're going like this, but they stay at the same distance one to the other. And so if a solid only allows rigid motions, then it's a rigid body. And you have to think of a hard solid, right? If I take this cube and I move it around, you can see the distance between, I don't know, those two edges is going to stay the same. And this is a rigid body. Okay. But now if the body is soft, then they might pull apart, come up together, and so on and so forth. And so I'm just going to write here this motion here, x plus q x, where c is a vector and q is a proper orthogonal tensor. I think I forgot to introduce orthogonal tensors in the online videos, but they are introduced in the lecture notes. Basically means that for this type of tensors, the inverse is the transpose. Right? QQT is I, and then proper means that the determinant is +1. There are two types of tensors that give you that satisfy this identity, and their determinant. Then you can see if I take determinant on the left, I'm going to get determinant of q squared. On the right, I'm going to get determinant of I, which is 1. So determinant of q must be plus or minus 1. Plus is proper, minus is improper orthogonal tensors. Yeah, if you think of a rotation, for instance, a very simple one, a 2D in the xy plane, this indoors example. It's easy to check that if I take the transpose of this matrix and multiply it by the matrix, I'm going to get the identity. All right. So I was digressing a bit here. Okay. So this motion I just defined above, it is a rigid motion. And you can guess that just by looking at it. C, that's just going to be a translation. Every point is going to move to x plus c, so it's going to just be translated by vector c. And then q is a rotation. In a rotation, distances don't change, right? But we can just prove it by computing the distance between 2 points, x and y, say. I'm going to write the distance squared here. And x minus y. So for little y, I'm going to have c plus q capital Y. And I can see that the c's are going to cancel in the subtraction. So I'm going to be left with q x minus y dot q. All right, and the last time we saw we can change, can swap the order of the dot product, provided we take the transpose of the tensor, right? UAV is equal to U dot AV is the same as V dot ATU, sorry. And now QQT, that's the identity. And so I'm left. So the new length is the same as the previous length. I've taken just any point in the solid, And so indeed, this is a rigid motion. So that was our first deformation, a simple one, and one we studied earlier when we did rigid body motions, of course. Okay, so these are the two important concepts: coordinates, configurations, and deformation. All those things are important in this course. Right, the potato on the left lives in the reference configuration. The potato on the right is the same body, but it's been moved and deformed and is now in the current configuration. I have to associate Lagrangian and Eulerian coordinates. I have to associate Lagrangian and Eulerian vectors, and also I have to associate Lagrangian and Eulerian differential operators. All right, and this is what I'm going to do now by introducing a very important object, the so-called deformation gradient. All right, so I should have written it here above. Gradient, curl, and divergence with a capital, that's with respect to xi, and gradient, curl, and divergence with no capital, that's with respect to xi. We have to define those operators. They're all about differentiating respect to a space coordinate, and so there's going to be two sets of them, one in the reference, one in the current configuration. The deformation gradient, by definition, by convention is called f. By definition, it's f equals gradient of little x. Its components, if I'm in a rectangular coordinate system, are those going to be of this form here. Remember, the gradient of a vector has those components. So the vector here is little x. Incidentally, this course is a nightmare to teach in the US because they write little x as a cross as well. Thankfully, in Europe, we do curly x's, so it's much easier. Okay, and then assuming the determinant is not zero, and I'll show you later why that is the case, we can compute the inverse is going to read as follows. F minus 1 ij xj. So that's not obvious. I just gave it to you, but we can check that it is indeed the case. So how do you check that two tensors are indeed the inverse one of each other? You just take their product and see if it gives you the identity. Check that f minus 1 is indeed the identity. So f minus 1, that's the product of two tensors. So we did that earlier. F minus 1 kj. Oh, I forgot to write the sums. Sorry about that. sum from k is 1 to 3. Yeah, so I'm just going to see if that gives me the identity. Fik, I've defined it earlier. And f minus 1, I just gave it to you as follows. X, k, xj. And now what do I recognize here? Nothing but the chain rule. Yeah, if little x depends on capital X1, capital X2, capital X3, here I've just used the chain rule to compute dxi, dxj. And then differentiating dxi respect to dxj, that's either 0 or 1, depending whether I or j are the same or not. So that is indeed the components of the identity matrix. And so that expression I gave earlier is indeed the expression for the inverse. So I had to introduce the deformation gradient because it's the tensor that gives you the link between reference and current configuration. And it gives you a lot of information about what's going on inside the body at the infinitesimal level. So is that assuming that the little x? Yeah, so the little x's are independent one of another, right? They are the coordinates. So that's all. Just think of them as x, y, z. If I differentiate x respect to z, I get 0. X respect to y, I get 0. But if I differentiate x respect to x, I get 1. And so that's the same idea here. Good question. Okay. Now let's look at this quantity here. F. Oh, just realized there's a typo here. Fik dxk. That's going to be dxk xk. Right, or if I want to write it explicitly, it's going to be dxi dx1 dxi dxi dx3. And here I can see that this is none other than the if component of the full derivative of dx. Yeah, what I've shown here is that f dx is d little x. Interesting. So you can see here by this important expression that dx, if you think of it as an infinitesimal line element inside the body, capital Dx, is transformed into d little x thanks to this linear mapping. Capital F, the gradient, the deformation gradient, is the linear mapping between line elements in the reference configuration and the current configuration. So I know that these are hard concepts to fathom, and now I'm saying all sorts of words that you are not familiar with yet. But if you think about it, f is dx, d capital X. You can see that f is the link between capital X and little x. But for infinitesimal deformation, infinitesimal segments. Okay. Showing how infinitesimal line element a line element is just a tiny segment inside the solid. Into line elements d little x. And indeed, f shows you how line elements transform one into another. It also shows you how infinitesimal areas and infinitesimal volume transform one into another. And we're going to see this in the next while. Another thing that f does, it makes the link between those operators. The differential operators in the reference with the capital error, in the current configuration with no capital error, f links them one to the other. So differential operators are linked as follows. For instance, the gradient with respect to capital X is linked to the gradient with respect to little x, the gradient of a scalar, as follows. The gradient of a vector is linked as follows. So it's hard to memorize those formulas. Usually you just find them in the notes or in the books. And then you can do the same for the divergence. Of a vector where j is the determinant of f, and same for the divergence of a tensor. Actually, yeah, I forgot to tell you, if you think of that box above, yeah, dx is not 0. A line element doesn't vanish, doesn't annihilate, so it means that, and mathematically it means that d little x is not 0. So f dx is not a 0 vector. That means that the determinant of f is not 0. So that's a nice proof of that assumption that I made earlier, that the determinant of f cannot be 0. F dx, that's a matrix times a vector. If it's not 0, it means then the determinant is not 0. So that's like a physically based argument to say that the determinant of f, which is often called j, is not 0. So those transitions from one reference or one configuration to another, some of them are easy to prove and some are not so easy. The first two are easy to prove. So the first one you will find the proof in the lecture notes. It's just a 2-line proof. It's quite easy. The second one follows from that. I think I put that in the problem sheet number 1. And the next two, they're much harder to prove. We'll prove them much later in the course, in the chapter, maybe the next chapter. I can't remember. Okay. So maybe nice point to break the recording.